My name is Andrew Davison. I'm going to be talking about the Kinect, how to program it using two libraries, OpenNI and NITE, using their Java bindings. Before I begin, how many of you have got a Kinect? All right, and how many of you have programmed with the Kinect? Oh, well, there's a few anyway. Well, you should all be programming. It's lots of fun. All right. So I'm going to start by just sort of, explaining the general hardware of a Kinect, and then I'm going to be looking at the two libraries, OpenNI and NITE. OpenNI is the basic library, which gives you access to things like the maps, which is the OpenNI name for the cameras. Also with OpenNI, you can access skeleton information about users who are standing in front of the Kinect, so you can access the joints. We'll see an example. Then I'll move on to a second library, NITE, NITE, which is on top of OpenNI, and that gives you extra functionality. In particular, it allows you to track hand points over time as you move your hands about. And also, it gives you a set of gestures as well, so you can use NITE to detect things like waves and circular motion of your hands. Then I'll finish off with two sort of examples of the Kinect in sort of unusual domains, one for computer vision and augmented reality. Okay. I can use this, can't I? All right, so here's sort of the inside of the Kinect. There's a lot of interesting stuff here, but my talk's just going to be focusing on the two cameras. There's an ordinary RGB camera. There's this thing here. But the more interesting one is the infrared camera. There's actually two parts to this. There's a source which sends out a pattern of infrared spots over the scene. Those are reflected back and detected by the infrared sensor, and depending on how the pattern of dots have been reflected, transformed, the Kinect can then transform that information into depth information, so it can calculate how far the user is away from the Kinect, how far the background is, things like that. So the infrared camera is used to calculate the depth information. There's other stuff too, like 4 microphones, a tilt motor, accelerometer. I'm not going to talk about those in this talk. Okay. All right, so here's the sort of basic camera stuff that you can access. That's the RGB camera as well, the camera that's sort of in the middle of the Kinect. Here's a picture of the infrared camera, the data coming back. This infrared information can be used to calculate the depth. Now, what gets back in the depth calculation is a series of millimeter distances, and then it's really up to the programmer to convert that array of distances into something graphical. And what I've done here is I've converted it into a series of grayscales, where white is for objects close to the Kinect, and black is further away. All right. Oh, I keep forgetting. All right, I've got, after seeing Simon's talk yesterday and today, I decided that risking live demos is a bit dangerous. So there's two demos which I really ought to do live. But the other 6 demos, I'm going to rely on videos that I recorded earlier. But they all do work, but I just don't want to risk the demo god's wrath by trying all 8 live. So I'm going to show some videos. All right. Okay, what am I doing here? Well, this is my PC back in the office, and I'm going to throw up 2 windows here. Let's wait until okay. Now, what's happening here? Well, I'm getting the depth information from the Kinect, and I'm converting it into 2 different forms. I'm converting it into a grayscale. You can see that my seat there in my office. And I'm also converting it into a histogram you can't really see the numbers here, but they're millimeter distances along the bottom. So, and the histogram records how many depth points are at a certain distance. So what this chart is saying is that most of the depth information is about 2 meters away from the camera at the moment. And this, of course, will change as I move into the scene. All right. All right. So I'm going to get up off my a chair now. Well, there's my hand. All right. I didn't bother getting up. I just lifted up my hand. And now my hand, if you remember, white means very close to the Kinect. And that's sort of reflected over here in the chart as well, because there's now a couple of data points at around about 70 centimeters. You can get about 50 centimeters to within range of the Kinect. That's about as close as you can get. All right. Let's carry on. I'm using a J3 chart here. Oh, that's something else I should mention. Let's just pause again. Oh. Back a bit. Oh yeah. You might notice here there's a sort of black stuff. What's this? Well, it's when the Kinect doesn't get back depth information. The black really means that there's no in-depth data for this part of the image. And that's something you have to deal with the Kinect. It's all built on top of reflected infrared. So if some of the infrared beams have bounced off to the left and right, then the Kinect doesn't receive the information and it can't infer the depths. So you often get images like this, which are very sort of blotchy, yeah, because it's not been able to return all the get all the depth information. Yeah, okay. So it's a little bit inaccurate, but it's okay. All right. Now what am I going to do? I'm using J3 chart here, so I'm going to zoom in on one part of the chart. And then I put my hand up again, and you'll see there's a big peak appeared around about 500 millimeters. Oh, I'm too slow. But anyway, there's a big peak appeared here. So J3 chart's quite nice. I know I should have used Java FX, but you know, I have J3 chart on my machine, so I use that. All right, I think that's probably enough. All right, let's move on. So how's this coded? Well, the good news is I'm only going to be showing you 2 slides of code. Maybe 2 slides too many, but I'm going to be relying on these sort of pictures to explain how things work. It's actually very straightforward, really. The programs are mostly just a loop. What you do before you enter the loop, you have to set up something called a context and generators. Now, there's a whole load of these generators. Image generator, which captures the RGB camera. Infrared generator, which returns the infrared information. And most useful, a depth generator. That's what I'm using to create the grayscale on the chart. So I use my generators. I'm going to use a depth generator, set them up here, and then I go into a loop, which basically just does 3 things. I wait for the context to be updated, which means that the generator returns some information. I then change that information, the map, into something else. In my case, I'm converting it into a grayscale and the chart. Remember, what is returned is basically a 2-dimensional array of numbers, depths, millimeter depths, and I have to convert that into something visual, the grayscale image. So I convert it, and then I just paint it into a J-panel. Then I go around the loop and wait for the context to be updated again. This happens every 40 milliseconds or so. All right. So here's my first slide of code. This is the initialization stuff. Again, maybe this is too much detail, but what it's showing is setting up the context. Then I create the generator, in this case a depth generator. I have to initialize it in various ways, in particular specify the size of the image that I'm capturing and the frame rate. Then I start the context off. It will now start obtaining information from the generators. In this case, there's only one generator, but there could be more here, as many as you like. We'll see more complicated examples a bit later on. This is the loop. So the last slide was the initialization. This is the loop that's going around. And there's essentially just 3 steps here. Inside the try block, we wait for the context to be updated, which will be when the depth generator returns information. Then this is my function, which I'm not going to explain, which converts the array of depths into a grayscale and the chart stuff. And then I update things. I should say, I'm going to be skipping over the details here, but if you want more details, you can have a look at my book, or you can go to my website, and I'll give details about that at the end. All right, when the loop eventually ends, for whatever reason, you have to close down the context to switch it off. And there's a lot of programs just like this one. All right, this shows some of the generators that you get in OpenNI. Remember, OpenNI is the library I'm using on top of the Kinect. And what I've just been using is a depth generator, and there's some other basic ones like image generator, infrared generator. Later on, I'll be using some of these more complex generators which do higher level information gathering. All right, well, let's do another example, transforming the user. Now, what am I going to do here? Well, I'm going to have the Kinect take a picture of the scene, and the scene is going to be split into 2 parts, the user and the background. The background part of the image is going to be thrown away and replaced by a static image. So I wasn't out in a forest when I did this demo, I was in my office. But the background of the picture has been thrown away, my office has gone bye-bye, and been replaced by a nice beautiful forest. Secondly, the user part of the image is transformed in different ways. And I've actually got a whole series of these transformations. I'm going to demo a few. But there's basically 3 sorts of transformations that I'm going to do. This transformation is a sort of global transformation where all of the user image is changed in the same way. In this case, changed into hexagons. We'll see the video in a minute. So that's a sort of global transformation of the user part of the image. The second sort of transformation I'll be doing is a time-based one, in this case a blurring. And this is a transformation which varies over time. In this case, more blurry, less blurry, more blurry, less blurry. And a third transformation, this isn't me doing a disco dance, I'm just standing still, but the transformation is using my center of mass. And the transformation of the image depends on the distance of the pixels, the user image, the distance of the pixels from the center of mass. And I'm sort of twisting the image, but it's twisting more or less depending on the distance from the center of mass. All right, examples. Okay, so I'm back to my office again. I've started up the application. There we go. Now, let's just... So, I'm not out in the forest. I'm in my office, standing around. I'm doing a global transformation. This is a marbling effect. So notice as I move about, the marbling carries on of being on me. But Alright, so that's me moving about. Now, what I'm going to do is select... Now, I should just mention something here. This menu has nothing to do with the Kinect. It's just so that I don't have to keep walking over to the keyboard. So this menu allows me to change the particular transformation without having to leave the Kinect field of view. Alright, So let's see what change I'm going to make. There we go. That's a blocky effect. Again, it's a global change to the whole of the user image. Block effect. Now I turn into Man of Chrome. So metal man there. Oh, there's something interesting you might notice here. Where's my head gone? You notice my head has disappeared off the top here. What I'm using here is the depth information, and if you stand too close to the Kinect, it won't see the top of your head. So really, I ought to be standing further back. So that just means I'm too close. So it's cutting off the top of my head. All right, Man of Chrome. So all those have been constant global change transformations. Now here's a time-based one where I beam in and out, fading in and fading out. So it's a time-based transformation there. All right, that's enough of that. Change. Come on, hurry up. So come on, down at the bottom there. Twirl. Right, I know I'm disco dancing here. I'm not actually doing that. I'm just stood like this, and it's doing the twirling for me. Oh yes. Now this is what happens when you have too many pizzas. Oh God! Now what's happening? What's happening here? Well, it's a lensing effect. So based around the centre of mass, it's making the pixels bigger round the centre of mass around my stomach, and less big round the side. All right, how does that all work? Well, it's a bit more complicated. I'm using 3 generators here. I have to use the image generator to get the image. I have to use the depth generator mainly in order to do some transformation of depth coordinates to image coordinates. I don't want to get into that. And the interesting one is the user generator, which returns something called a scene map. And the scene map basically is a series of integers, 0 representing the background of the scene, and 1 for a user. And if there's more than one user, you'll have integer 2 for the second user, integer 3 for the third user. And what I can do is I can use the scene map to very easily subtract the background, because everywhere where there's a 0, over on the image, I can just erase the image pixel, so leaving just me with no background. What I'll do subsequently is replace this empty background with that picture of the forest. Now, what about the user? Well, now I do the filters, and the thing is, I'm not actually doing any coding here. All the filters I've used, I've actually got from the JH Labs site. They're just standard, very nice, standard filter, Java 2D filter ops, which I've just used, and I apply to the user image, turning me to metal, making me twirl around. Yeah. And then what I do is I recombine the modified user image with the forest background at the end. All right, what's the program look like? Well, I'm not going to show it you, but it's a loop again. So I initialize this time 3 contexts: depth, image, and user generators. Then I go into a loop just like before. The only difference is, of course, it's a little bit more complicated. I have to do more changes to the image, and I have to combine 2 drawings when I repaint. I have to draw the background image and the modified user image, but it's really just a loop going around. All right. Now, let's move on. I'm still on OpenNI. What I've said so far is about how OpenNI can give you access to the camera, image, infrared, depth, and things like user generator. Now I'm going to talk about skeletons. Very nice, this. OpenNI can return information about the joints of a user. Currently, it returns information about 15 joints, things like the head and neck joint. The information it returns is the position in the scene, X, Y, Z, and also rotational information as well. So you can get that for each joint. All right, you can use this for all sorts of nice stuff. Right, what am I going to do? Well, what I'm going to do is basically modify my previous example, but instead of changing me into Mr. Twirly, what I'm going to do is I'm going to find my head joint and neck joint and replace me by someone who's much uglier than I am. Every talk about the Kinect that I've ever seen always mentions Minority Report. So I've got it back in here. Yes, so anyway, and let's do the demo. That's sort of fun. Where's it gone? There we go. All right, back to my application. So I start it up. Now there's an interesting little thing I have to do at the beginning here once it starts up. This is loading up all the various images. Right, you'll notice my head's the same. Yeah. Well, when you're using the skeleton information in OpenNI, up until recently, you have to calibrate the skeleton first, which means that you have to initialize it, and you initialize it by assuming a standard position. I surrender position or psi pose. You have to do this so that the OpenNI can detect your skeleton, initialize it, and then after that it will follow your joints around as you move. So in a moment I'm going to assume the psi position. All right. There I go. All right. Now it's tracking my joints, and now I can change my head to something. Tom Cruise, there we go. There's something evil being detected. Some evil presence. We should arrest him immediately. Yes, all right, Tom, that's enough of that. All right, I've got that. Change, please. All right, what shall I choose now? All right, go. Probably more accurate for me is Mr. Bean. Notice it follows me around, okay? All right, I don't want to be Mr. Bean anymore. I'll be back. Yeah, there we go. Oh, look, Arnie's... No, it should have been Skynet, not Microsoft. He's blown up the wrong place. All right, now this is a bit like a blue screen, but it's a feature, not a bug. It's a feature. There's one word that I have to explain here, and that word is developers. All right. So, hours of fun. Yeah. All right. So, how does it work then? Well, the application's getting more complex. I'm still using the depth, image, and user generators, but the user generator I'm using in a more complicated way. I'm using two capabilities. Pose capability is, I need that in order to detect my I give up position, the psi pose, and the skeleton capability is used to build the joint information, head, neck, and so on. What are these yellow circles? Well, the way OpenNI works is that you have to attach listeners to the various generators and capabilities. These listeners are woken up when various events occur, such as when the calibration finishes or when the skeleton moves. And then you can have Java code in these listeners, which is executed. So there's an awful lot of listener code everywhere in the more complicated applications. You still have the loop going around, but you also have all this extra listener code attached to the skeleton capability, the pose capability, and so on. Okay. So listeners, lots of them. All right. Maybe what you didn't notice there, maybe, is that when I was moving around, the head was moving as well. In fact, it can rotate. It rotates only in the around the z-axis, sort of like this. And the way I did that was I used two joints, did a bit of simple trig, and calculated the angle based on the rotation between the head and the neck joints. I could have used the OpenNI rotational information, but it's a bit tricky. It's all sort of matrices and stuff. And so for something simple, for simple rotations, it's easier just to look at the joint positions and do the math yourself, working out the rotations, the angles. All right, let's move on to something a bit more tricky. What I was using in that last example was actually just two joints, the head and the neck joints. Well, now I'm going to use every joint. Now, what's this? Well, of course, there's only me here, but the Kinect is actually capable of detecting up to 4 people. And this screenshot was taken when there were 2 of us, me and the other guy in my office, stood in front of the Kinect. Each user is going to be converted into a 3D model in this artificial world, and the joints of these models move following the joints of the real user. Now, I think this example I need to really sort of demo it for real. So let's cross your fingers and try demoing this one for real. Okay, now just as with the user, I have to assume the side position so it can calibrate me. I'm over here. Hello. Ah, there we go. We are sailing. And I can turn round a bit and things. Now this 3D world has got a camera which I can rotate. So I'll just move over here. A bit tricky. There we go. So the camera, it's a bit hard to visualize, but the camera's moved over to the right-hand side now. Now, where have I gone? Well, as soon as I move outside of the Kinect's field of view, it loses my joint information, because I'm not there anymore. So you have to decide what your application is going to do when joints disappear. And what I decided to do was simply make my 3D model disappear. So let's move back into the scene. Come on, now I'm back. It should be seeing me. So maybe I have to do the side. Ah, there we go. So the camera is sort of over here now. Yeah. So it's a bit hard to you see. There we go. Something like this. Right. So there we go. So it worked. Worked okay. All right. That's my first live demo. I've got one more live demo that I'm going to do. All right, how does it work? Well, the code is actually pretty much the same as for changing the head. So I have to use skeleton and pose capability to initialize calibration. And these yellow things, remember, are the listeners. And the most important listener here is the listener which is fired when calibration completes. That's when the skeleton is initialized. And what I do here is I then create my skeleton object in the 3D world. And then after that, as I move, the joint information is then used to update the skeleton in the 3D world. All right. But as far as programming goes, it's the same as last time. It's a whole load of listeners and the same generators and capabilities. All right, well, that's OpenNI dealt with. So remember, OpenNI is the sort of basic level library on top of the Kinect. It gives you maps, user generators, skeletons. Now I'm going to move to NITE, which is another library on top of OpenNI that gives you extra stuff, hand points. Now, you might think, well, why do I need hand points? Because you've already got that with the skeletons. Well, it gives you the information in an easier fashion, less coding required. So hand points. And it also gives you gesture information, like, oh, that's a wave, that's a push, or a click. Yeah. Let's do the examples. I've already said that, so let's skip that. All right, how's it all work then? Well, it's based around detector classes. Each detector class detects a different gesture. So, for example, wave detector is for detecting waves, guess what? Circular detectors for detecting circular motion. And they're all built on, they all extend a basic class, point control, which is detecting basic hand position information. So you can use the basic class to just get hand points, or you can use the subclasses to get different, detect different gestures. All right, so what am I going to do here? Well, I've built myself a whole new GUI, a gesture GUI. My gesture GUI has 3 GUI controls, a button, a slider, and a dial. Now let's go back to the video. Alrighty. It's not starting. Come on. I command you to start. Oh, I know what it is. Maybe not. There we go. All right, so I'm starting the program again. Okay. So you can see how happy I am here. Oh God, 10 hours trying to get this to work. Now, I'm using the NITE library now, and I'm doing gestures, and it's the same sort of thing. You have to have an initialization gesture in order to get things going, just like you had to calibrate the skeleton. With the gestures, you have to do an initial gesture, which usually is a push. So you're going to be seeing me doing this to try and get the thing to start working. That's why I look so miserable. So I do the push to start the gesture recognition. All right. Wait. Oh, I pressed the wrong button there. There we go. P. All right. All right, so I'm going to start pushing. That's me pushing to get the thing going. Yes. Now I move my hand up to here. Now what's happening? Well, when it detects my hand in the same location as the button is selected, which means it turns yellow. If I keep my hand in the same position in space for about 2 seconds, the button will be pressed, which it'll turn green, and also in the code it returns an event saying button pressed. You don't see that because I'm only showing you the window, but anyway. So there you are. Now I'm moving to the slider, and it's the same sort of idea. When my hand's detected over the slider, it is selected, it turns yellow, and the blue tab moves with my hand. If I stop moving my hand for about 2 seconds, the button it's activated, and a little yellow circle appears. In the code, what also happens is that an event is sent out which records the position of the tab. All right, so I'm moving my hand about. Yeah. All right, when I stop for 2 seconds, that's enough. Stop your hand. Yes. It will go, it's selected there. Now I'm over to the dial. And again, it's the same sort of idea. It's selected when it's yellow, and then as I move my hand around, the dial will change. I've got this little hand here, but actually the important thing is the black line. If I stop moving my hand for 2 seconds, the dial is activated and an event is sent containing the position of the dial. Now, I've coded all of these myself, but I'm not going to show you the code. But all the 3 GUIs subclass a basic GUI panel class which deals with this selection and activation. It's this basic sort of state diagram implemented. And then I subclass it to have these different gesture GUI controls. The details are on my website or in the book. Alright, so I move it around, stop for a bit, click, so it was selected. Now I move back to the slider a bit. Alright, stop. Activated, okay, now over to the button, stop for a minute. Activated. Oh yes, so that's that done. Alright, how's it all work? Well, we're going to see different coding now because I'm using the NITE library. And the NITE library uses different generators. It's a while since I talked about the generators, but I'm using higher level generators here, hands generator and gesture generator, and you can guess what they're doing. The hands generator returns hand point information, and the gesture generator returns gesture information like the push and the wave. Yeah, you pipe these through a session manager which directs the information to different controls, and you implement things using lots of listeners. So for example, for the hand point, when a hand point is detected for the first time, a listener is fired. When a hand moves, a different listener is fired. When a hand is lost, so the Kinect loses your hand, another listener is fired, and you code up different things using those listeners. Yeah. All right. All right, that's NITE finished. So that NITE gives me hand points and gestures. Now let's move over to using the Kinect in sort of slightly different application domains. I'm going to look at computer vision, augmented reality. All right, computer vision. Well, what I'm going to be doing here is using a really wonderful computer vision library called OpenCV. In particular, I'll be using a Java binding of OpenCV called JavaCV. And it does everything. Where does the Kinect fit into this? Well, it's being used as an input device. You know, I can supply it with, I can use the Kinect to supply image information or infrared information, or in this particular example, depth information. I've had students working on different projects like this, such as motion detection using the Kinect, face detection and recognition. In fact, this screenshot is an example of face detection. It's found my face with a bullet with crosshairs over it for shooting me. So that's detection. And down at the bottom here, maybe you can't see it, but it says recognized Andrew. What it does is it sort of compares the picture against a database of images and decides which person this is. That's the recognition part of face recognition. All of this is using the Kinect as an input device. All right, well, I'm not going to do that. I'm going to use hand recognition. Yeah. So the idea here is I'm going to put my hand in front of the Kinect, and it's going to detect my hand. And more than that, it's even going to be able to work out which finger is which. Now, I should say, again, it's a little bit approximate. So, for example, here you can see there's two problems. It's not detected my little finger. That's what the red circle means. And it's also decided that this is a finger as well down here. So you've got to accept this when you're doing computer vision type stuff. There's a sort of trade-off between accuracy and speed. And if you want things to be happening in 50 milliseconds, you've got to accept a certain amount of error in the analysis. All right, so let's just run the video. All right, so I'm sat in front of the Kinect and I move my hand in front, and it finds all the fingers at first, and I'm moving my hand about. Notice there's a few little problems. Oh, actually that's okay, I missed that bit. Let's move on a bit. I have to stop when there's a problem. No, that's okay as well. You can't really read the blue, it's too blurry, but occasionally, for example, it will decide that I've got two thumbs, or it will put the middle finger in the wrong place. sometimes it will detect extra fingers. Yeah, but it's not too bad. Yeah, this is real speed. I'm not speeding up the video or anything. Yeah, it's the actual speed of the analysis. It's detecting a few extra fingers there. Oh, it's lost my thumb. Wait, and now I've moved my hand away. Now back again. It's decided my index finger is my thumb. Moving around a bit. It's not doing too badly. Yeah, but the point about this is that there is some error there. All right. Now, how's this being done? Well, the Kinect part of this is actually quite minimal. What I'm doing here is I'm using the depth map, which, remember, in the basic approach is just a series of grayscales, white for something close, and then dark grey, black further back. So that's what I'm supplying to OpenCV, Java CV. And then I'm using a whole series of built-in functions for cleaning up the image. So I threshold it, that's a built-in OpenCV operation, to cut away the darker greys and the blacks. Then I smooth the image a bit to get rid of all the blotchiness. Remember, OpenNI often returns an image which has black blotchy bits around the edge of the image. Smoothing cleans it up a bit. Then I find the biggest contour, the biggest shape. All of these operations are OpenCV, not Kinect, not OpenNI. Then I switch over to finding the convex hull, polygon around the outside of my hand. And then I find the defects in the convex hull. The idea here is that the sort of pointy bits will be where my fingers are. So this is where one finger is, that's where another one is. Yeah, and it actually tends to get it wrong. So what we see here is it's decided these are my fingertips. Oh, that's good. But it's also decided that this is a fingertip, and that's a fingertip, and that's a fingertip. So the information it returns is a little bit wrong. So you have to go through a bit of a clean-up phase, and there's a whole load of techniques for cleaning up the data to try and make it a bit more accurate, which I won't go into. Yeah, so you end up with the fingertips, and then there's another issue as well, which is, of course, my hand can be rotating, and so you have to sort of ignore the rotation information. So that's my thumb, and if I rotate my hand, that's still my thumb. So you have to sort of undo the rotation effect. And finally, you label the fingers. Now, I should say, as it stands, my code's a little bit on the hacky side. I'm going to have a student, I did this for this talk. I'm going to have a student working on this next semester to improve this stage to make the identification of the fingers better. What am I going to do with that? Well, the next step, which my student's going to do, is I'm going to use it for doing gestures. Yeah, so if you can identify thumb and forefinger, index finger, then you can do things like pinch and zoom and rotation. Yeah, so even if you only identify two fingers, it's useful for doing gesture type stuff. And all this is based on just holding my hand in front of the Kinect. Okay. Now let's move on to the second application. I think I'm gonna. Have I got time? I'll use the video here. This is augmented reality. Now, what is that? Well, it's it's Google Glasses. It's a scene, the real world scene, and somehow it's augmented with computer information. The way it works is that the library finds a marker in the scene, and then it uses that marker to add a 3D model to the image. Let's just run the video. It's clearer if I run the video. Okie dokie. So there's my marker, and you'll see that as soon as it detects the marker, it will then draw a model. Now, as I move the marker about, the library will calculate the marker's position and rotation. That's then used by my code to position and rotate a 3D model, which is drawn on the front of the image. All right, so there's a few libraries working here. The Kinect is being used to get the camera. I'm using a library NYR toolkit to do the augmented reality, which means finding the marker, extracting the position and rotation. And I'm using Java 3D to draw the 3D model using the position and rotation information. All right, let's move about a bit. All right, now you'll see again it's a bit flaky. Let's see. All right, well, in a moment. Come on, go! Too fast. Let's just go back a bit. Did you see that? It went wrong a bit. Where is it? It was very quick. There we go. What happened there? Well, again, these libraries, work fast, and sometimes they make mistakes. What's happening is that NYR toolkit, for some reason, has lost track of the marker, and it's generated the wrong position and rotation information. It's then passed that on to Java 3D, and Java 3D has drawn the model at the wrong position. So it all depends on the library being able to track the marker. But most of the time it works okay. All right. So, let's quite finish there. All right. So, all right. Yeah. So move it about a bit. It went wrong there. Yeah. Move around. And you notice as I step towards me, please, Andrew. Andrew, step towards me. Thank you. As he comes towards me, since the marker is getting closer to the Kinect, the model gets bigger as well. Yeah. All right. How does this all work? Well, again, I'm not going to show you the code. The Kinect is actually doing very little here. It's just supplying the RGB camera information. Having said that, implementing this, which is passing the camera image over to the NYR toolkit library, is actually quite tricky. There's sort of issues with threading and things. But anyway, it works. NYR toolkit finds the marker in the scene. It then calculates the position and rotation of the marker. Then it passes that to Java 3D, which has a model loaded. And then Java 3D modifies, positions, rotates the model, and draws it in the scene so it matches up with the marker. Another way of looking at this is that from the user's point of view, you have the picture which was generated by the Kinect, and Java 3D is sort of drawing a model in front of it. So it looks like it's sort of augmenting the reality by adding the model. All right. So, at the end. So, what have we looked at? Well, what I've talked about is two libraries. So, on top of the Kinect, there's OpenNI. That's a basic library which gives you things like access to the cameras, things like the RGB image, the infrared image, the depth image. It also gives you more high-level things such as scene information, so the background is zeros and the user is 1. It also can give you things like skeleton information, joints, where you are in the scene. Quite useful. Then I also looked at a higher-level library, NITE, which is built on top of OpenNI, and that gives you things like hand points, so it will track your hands as they move around, and more high level, it'll also detect particular sorts of gestures, waves and circles. And we looked at sort of many examples. Well, I've got one last example to do. Oh no, I haven't. This slide first. What have I not talked about? Well, I've not talked about lots of things, actually. For example, I didn't talk about the accelerometer, which is in the Kinect, or the microphones, or the motor. Actually, the tilt motor is a bit of a joke. If you look at the tilt motor inside, it's these two little plastic gears, which are pretty useless. But anyway, a tilt motor. And the microphones are quite useful. The microphones are on either side of the Kinect, so you can do things like beamforming, which is basically using the microphones to detect the rough position of the user based on the noise they're making. You can also use the microphones as input to Java libraries, such as speech recognition. Yeah. Also, I didn't talk about games, which is my particular example. I did a Kinect version of Breakout. I think I've got time to show that. Quickly show that one. All right. So here we are. This requires me to. Yeah. What am I doing? Get back over there. Oh, turn on the music. Right. Now I have to, this is using gestures, so I have to. Now what's happening is that my hand is moving that little trolley at the bottom, and hey, over there! Right, there you go, and the ball bounces back up, and yeah. So it's based on my detecting my hand movement. It's not the most exciting game, but anyway, it shows it working. All right, that'll do. Now, if you want more information about this, you could either pay money and please buy my book, which is in the bookstore, very cheap, yes. But if you don't want to spend any money, you can go to this URL and draft chapters, and all the code can be found at this URL if you want to download it and try it out. Okay, now my last real example. Okay, one last example. Let's see if I can get this to work. Let's close this off. All right. Take a little while to start. Okay. That's using Java FX for the music. Come on! I'm over here. In a minute, a window will appear. Window, come on, window. This is why it's always a good idea to video everything. Window! I want the window! Thank you. Right. Now I have to assume the side position. Right. Now, you have learned about the Kinect sensor. But now you will pay the price for not buying my book. Yes, young developers. Come on, come on. Yes, young developers, you will die! Yeah, that's actually all it does, actually. Thank you, that's it. All right. So I haven't actually done any questions. Are there any questions? Yeah?
What's the outside range for the kinetics on the distance information?
Well, my office is very small, so I'm not quite sure. No, officially it's 3.5 meters. That's the extent, but I've never really tested that. Certainly the closest is about 55 centimeters for the OpenNI anyway. Yeah.
So the question about calibration. Can those libraries let you calibrate as you're moving instead of having to assume a position?
Well, the next version of OpenNI is meant to not require you to assume the side position. It's meant to be able to calibrate the skeleton just when you walk into the scene. But the version of OpenNI at the moment requires you to go like this. And it's a standard position that you have to assume. The SI is hardwired in. It's waiting for you to do this. Yeah. Yeah.
So earlier in your code example, you had this license thing. I thought the whole thing was open source.
Well, Simon mentioned this the other day. Yeah, it is. Well, to be precise, OpenNI is open source, but NITE is not. NITE is free, but it's not open source. And I don't really know why they include the license, because it's freely available. It's always the same code that you have to type in. I don't really know why you have to do it, but you do. You have to include the license. Any more? Yeah.
Just go back one slide.
Oh yeah.
Thank you.
Oh yeah. Yeah.
When you're doing your hand gesturing, how far away was the hand from the...
Oh right. It was as close as I could get it. So in my office, I'm sat here, and my hand's about 60 centimeters away from the Kinect. Yeah.
Is there hardware and software on the Kinect, or is it just strictly a hardware, like on the actual?
Oh yeah, yeah. It's doing the conversion of the infrared to the depth information on the camera.
So then none of that, like that zeros and ones picture you had, none of that's happening on the Kinect device. It's either happening on your PC or on the Xbox or whatever.
Yeah. Well, the zeros and ones, that's the scene generator. That uses the depth information, and it's done by OpenNI. So the Kinect is supplying the depth information, and the rest of it's being done by the OpenNI libraries.
Or the Xbox.
Yeah. Whatever library you're using, yeah. Yeah.
Some sort of driver, I mean, I assume it's a USB input.
Oh, yeah. That's one of the sort of nasty bits about using OpenNI. You have to actually install 3 different drivers in order to get it. There's a low-level driver for the Kinect. Then you have to install OpenNI and then NITE. Actually, that's not true. You have to install OpenNI first, then the driver, then NITE. Don't know why, but that's how it is. Yeah. Yeah. Yes, yeah, and Mac as well. Yeah.
Does it lose your skeleton when you turn your back to it?
Well, it's a bit flaky. What happens is that if you're lucky, it will not lose you. But as you turn, your part of your skeleton is hidden. Yeah. So if I'm stood like this, it can't see this arm, yeah, and it can't see this leg because it's being obscured by this part of my body, and it can then lose those joints, and it's sort of a bit iffy. If you then go like this, it might see the limbs, might see the joints again, or it might have lost them. You have to move quickly. So it sort of depends.
So, quick follow-up on that. It seems like, I don't know, is there anything that would prevent you from using multiple devices, interpolating, or having them both in order to clean up the...
Oh yeah, you can do stuff like that. The people have actually developed that sort of techniques on top to improve things. I didn't bother doing that. They're just demos. But there are various tricks you can use for sort of dealing with the errors, the approximate information. Yeah. Yeah.
You have one more question. Is this the only Java library, or are you
No, there's a few. There's a few different Java libraries for the Kinect. But I've only used this one, so I wouldn't like to comment on the others. But there's several.
Can you name anything?
Yeah, there's an interesting one. There's apparently a Java binding which is going to be on top of the the Microsoft SDK. I think it's called JNet. No, yeah, something like this. If you do a Google for Java and Kinect, you'll find all of them. Yeah.
The infrared map fits the RGB map exactly, because in the past there were some issues that the maps are not fitting.
Oh no, they don't. They don't. That's something I sort of glazed past when I was talking about it. The two don't match up, so you have to, in your code, specify that the two should be matched up. You have to change the viewpoint of the depth map so it matches with the image map, and they don't actually match up. The depth map turns out to be smaller than the image map, even when you line them up. So they're not the same size. The depth map is smaller.
Is it hardware limitation or software?
Yeah, hardware. All right. Oh yeah.
Are there any places where you can see what other people did in terms of the product ideas and so on?
Oh yeah, there's a really nice website called connecthacks.com that has lots of nice screenshots of things. Yeah. Type into Google Kinect hacks. You'll find lots of them on YouTube actually. Lots of fun ones. Lots of great fun possibilities. Well, one more.
I'm kind of interested in eye tracking. Is there anybody who's just really rocking that right now?
I am. Well, my student is.
Oh, wonderful.
But, well, it's not so great actually, because you're going to have to sort of sit like this. Yeah. So it's perhaps not the most practical approach. Yeah. So, and the trouble is really, well, the results we've got have been very iffy. Yeah. It really depends on OpenCV. There's various techniques you can use. Yeah, but if the image isn't really, you have to, for example, you have to shine an enormous bright light onto your face so that you can improve the contrast of the picture. But it's not that great, really. Yeah.
So what if someone creates, an awesome product, and what are the options for them to monetize it? I would imagine that Microsoft probably wouldn't let you use this in your product that you are also selling. Has anyone reached that space yet?
I'm not really want someone to ask about the commercial aspects of things. I just do fun stuff. But there are certainly there's certainly a lot of stuff on GitHub and SourceForge, sort of open source examples. But I'm not sure that you make any money out of it.
Doesn't Microsoft not even actually? They're not the ones who invented the technology to begin with, right? It's
No.
Israeli company that-
PrimeSense.
Yeah, PrimeSense.
Yeah, so they're the people who've actually released the driver for the, and they're the ones who they're the ones behind OpenNI library and NITE.
And doesn't Asus, they have their own?
Yeah. Asus is the other device that can use Open. I didn't talk about this. OpenNI is meant to be more general than just for the Kinect. It's aimed to be used for a range of different devices which can detect movement. Yeah, but there's really only two at the moment, the Asus device and the Kinect. But that'll change. Okay. So, don't forget to buy my book! Okay, thank you.